Hi there! Welcome to a new physics lesson filled with adventure and discovery. Today, our topic is harmonics. And so we're going to take a look at what is a harmonic. We're going to take a look at how harmonics play a role in vibrating strings, in open-ended tubes, and closed-ended tube instruments. And then we're going to look at how it applies practically to what we call the timbre of different instruments, and also what happens when instruments are not quite in tune or in harmony, and we get these beats. What does that sound like, and why does that happen? So we're going to take a look at that today. And so let's jump into it. First of all, what in the world is a harmonic? I have a quick video that kind of demonstrates what a harmonic is and this is from the World Science Convention. So here we go.
So I'm going to play that low note again, okay? And then I'm going to blow a little bit harder and see if I can find those other frequencies that this tube likes, okay? So I'm not going to change my fingers. And if you've been watching up here, this is kind of fun to watch, right? You can just turn this on at a party or something and have a little fun. So what we're seeing here is it's kind of like a frequency finder. So this program is picking up what frequencies are being heard in the room. So if I play the flute one more time, just to see this lowest frequency that I'm actually playing, okay?
All those spikes are other tones that are being played at the same time?
At the same time. So your ear is great. It says, well, I know that the highest one.
We think we're only hearing the first one on the left.
That's right. It's exactly right. So your ear says, okay, I understand that this frequency that I'm playing is around 500 hertz, if you look at the bottom line here. And the highest one, the strongest one, the one that your ear understands is the note, is that first one, okay? But what makes it sound like a flute, what gives it its tone color or timbre, as you may have heard before, is the fact that you have a lot of other things happening that you don't really perceive as being the note. But it also means that if you follow, as I play here in a moment, if you follow, I'm going to play the low note. As I blow harder, I can actually play on that second highest peak. Okay, and these are called harmonics. Try again. So as I blow harder and harder, I'm actually going up onto those different harmonics.
Okay, and so I don't know if you caught that, but when this lady is playing the flute, and so here's the picture of it. When she's playing the flute, although our ears hear one note, it sounds like there's only one note, and that's because it's the most frequent pitch. The flute is actually playing some other notes, and those other notes are what we call harmonics, which is really cool. And so that's kind of an introduction to harmonics. Harmonics, hopefully you see the word harmony in there. A harmonic is other notes that contribute to the harmony of that main note. So like when you sing in a harmony, or when you're singing a harmony with another person, you're not singing the main tune, but you're singing a little bit higher or lower to support or to kind of make that main tune or that main note more beautiful. And so that's the same thing with harmonics. Harmonics are all these different other pitches that are supporting that main pitch. So kind of interesting. So recall that yesterday, or in the last lesson, we talked about what we call the fundamental frequency, and that every single object, whether it's a beaker, okay, or another beaker that's smaller and has water in it, okay, they have a fundamental frequency. They have a fundamental note. So this beaker has a fundamental frequency that if I hit it, it makes that same note every time. And also recall that we have the wave equation. So we have wavelength is equal to the frequency, the speed of the sound, or the speed of later on light is equal to the wavelength times frequency. And so our frequency, we can flip it around and say that the speed of, let's say, this vibrating string or the air moving through the flute divided by the wavelength will give us the frequency. And so notice for a vibrating string, we're going to talk about vibrating strings first. The fundamental frequency is going to be two times the length the speed of the string divided by 2 times the length. Okay, that's going to give us the fundamental frequency of the vibrating string. Or notice if we put this into kind of this diagram here, we can find the fundamental frequency by dividing the wavelength of that string. Okay, so harmonics are these interval what we call notes or frequencies that's like again support that main fundamental frequency. For the flute, it's that really low C note, and then there's all of these other spikes of all these other frequencies that support that main note. So same thing with strings. Strings, whenever you add half a wavelength, you get the next blip, or you get the next harmonic. And so on my guitar here, if you take a look at the guitar, okay, we have all these frets which kind of give us the different harmonics of a certain string. So when I pluck a string, okay, I get the fundamental frequency of that string. Okay, that's the fundamental frequency of the string at that certain tuned frequency. However, if I divide the string in half, which is these 2 dots right here, is the kind of the midway point, I'm gonna get what we call the first harmonic, or the second harmonic, okay, which is pretty cool. Okay, so I don't know if you can hear it. Oops. Okay, so that would be the second harmonic, which is pretty cool, of that string. Okay. And then again, if we divide that even further, if we go 2/3 the length, we get the third harmonic, and then if I divide it into 4, I get the fourth harmonic. Okay, and so what's the reason for that? Well, every time we make the string shorter at a certain point, we get these different harmonies on the string. We get these different notes that support the main note of that string. Okay. So how could we find the harmonic of a vibrating string mathematically or in physics? Well, if we can get the frequency, okay, and we can use this equation. Frequency is equal to the harmonic number, so the harmonic number could be 1, 2, or 3, okay, depending on which harmonic you're playing, and that's times the speed of waves on the string divided by 2 lengths of the vibrating string, because that's the fundamental frequency of the string. Okay, and we can find what that frequency is for that string at that harmonic number. Okay, so pretty cool. Next, we have open-ended tubes. So that's one example of that would be the flute. The flute has, although you're playing into it, it's open on both ends, and so it's an open-ended tube. And it's a little bit different from strings. All harmonics are possible on an open-ended tube, and half of the wavelength forms in the open-ended tube. So what does that mean for us? Well, okay, so the example is a flute. So notice these 2 black lines are like the flute, and half a wavelength can travel in that flute, and that would give us the fundamental frequency, or what we call the first harmonic. So that's the low C that girl is playing on the video. However, if she blows a little harder, she can actually get to the second harmonic, or what we call the overtone, the first overtone. And so notice, how do we get that? Well, you get that by adding another half a wavelength of the vibrating sound waves. Okay, and so how do we put that into an equation? Well, same thing. The frequency, or Fn, is equal to the harmonic number 1, 2, or 3, depending on what harmonic number it is, times the speed of sound in the pipe divided by 2 lengths of that column. Since whenever we're playing the flute, it can only give us half of a wavelength there. Okay, and inside of only half of the wavelength can travel in there. Okay, so just as another example of that, so this would be playing the flute at low C, and then if we play the next, if we blow a little bit harder, we can get a high C, okay, or a higher note, which is, notice it is, we're dividing this wavelength into half. And then just like the string instruments, we can go even higher, and we can get another wavelength in there, and then so on and so forth. We can go higher and higher and higher, okay, for the flute. Now closed-end tubes, another category of instruments, musical instruments, are closed-end tubes. So this would be the example of, say, a clarinet. And so if only one end is open, only odd number harmonics are possible, which is really interesting. And so only 1/4 of the wavelength forms in the closed tube, as opposed to half in the flute. And so in a pipe with a closed end, we have a slightly different equation. So since it's only 1/4 of the wavelength, notice we have 1/4 the length of the pipe. We have the velocity of the sound in the pipe. Again, the harmonics, and notice it's only going to be odd harmonics. And this is the reason why if you're a clarinet player or like any kind of clarinet player, you sometimes come across these squeaks like ooh, squeak, right, for these clarinets. And the reason for that is because one of two things: either you're playing a little bit too hard into the the clarinet, and so it's moving to the next harmonic, which is kind of this high squeak noise, or possibly one of the holes is not closed on when you're fingering your instrument. Okay, and so yeah, it's really interesting how the clarinet can only get up to these odd number harmonics. Okay, so here's an example of the clarinet, close, and notice this is the fundamental frequency of the clarinet. And if we blow really hard, we'll get that squeak noise, which is way higher than that fundamental frequency. It skips to the third harmonic, what we call. Okay, so the clarinet continually skips to the odd number harmonics. Okay, and so this brings us to our practical application of timbre. As the girl is showing, when she's playing the flute, although we hear one note, there's several other spikes of different frequencies that are kind of in the background or in harmony with that first note. And those harmonics contribute to what we hear as a sound of the flute. The flute sounds way different from, say, the sound of a clarinet or the sound of an oboe. Okay, so I have an oboe here and I have a clarinet here. And notice the frequency, if I play the same note for each of these instruments, the different harmonics or the different frequencies give us these different sounds, which we can distinguish as the flute or the oboe or the clarinet. So harmonics account for the sound quality or the timbre, and the timbre is that quality, that sound that makes it sound like a flute or like an oboe or like a piano or like a guitar. Okay, but really it's these different other harmony frequencies that are contributing to that one main frequency. Okay, so viola and the clarinet can play the same note, but they sound completely different because of these different harmonics that are also played at that same note. Okay, so really interesting. So here's another example. We have a tuning fork. A tuning fork only plays one frequency. It only has that fundamental frequency, just like these glasses. Okay, they have that one frequency. Okay, but if we have a more complex instrument, say the clarinet or the violin, because of the way they're built, although they have one main frequency, there's other frequencies that are played. There's other harmonics that are played. There's other frequencies of sound that hit our eardrum that we hear. Okay. Now, what happens if we have two instruments that are the same instrument but slightly out of tune? And you might experience this in Mr. Shimizu's class, or if you're playing in an orchestra, or even if you're singing. When you have two wavelengths of different frequencies that are not in harmonics, that are not a harmonic, they start to interfere with each other. So notice if I have this red wavelength here, and then there's somebody else playing this second wavelength here, this blue wavelength, there's going to be times in which the waves interfere with each other. Sometimes they're going to combine together, and sometimes they're going to cancel out each other. And so what we get is what we call beats. We get these and I'm going to play something in a moment. You're going to hear this wow, 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 wow sound. And what that is because the two notes are not at the same frequency, they can build off each other, and they can cancel out each other at certain times. Okay, and so you're going to hear like a loud, soft, like wow, wow, like a kind of like a dampening noise. Okay, and so I'm going to play it for the guitar. Let's see if you can hear it. So that's one note. I'm going to play another note, okay, different frequency, together. Okay, might hear that. Okay, do you hear that sound? Okay, those are the beats. Okay, and he's gonna play it one more time, and you're gonna see that as he tunes the guitar, they can get closer and closer together. So you get really fast, or they can get farther apart when you get and the yeah. So here, let's hear that. Okay, so you can hear it going really fast. He's gonna do it one more time. So notice that one you can hear the okay, and so those are beats that happens when you have two different frequencies playing together. Okay, all right, and so that's our lesson on harmonics. Hopefully there's something that intrigues you or helps you to better understand your musical instrument better. And so thank you so much for joining us, and we'll see you next time.